Hi, I'm Mikhail Hirschfeld. I'm here to talk about part 3 of my project, in which I finalize the exploration of my data and begin to construct my model. So to recap, my academic and professional experience has given me a really strong interest in the domains of mobility and vehicle safety, especially with working with geospatial data. So my goal with this project is to be able to predict accident severity based on defined on traffic delays from a data set of 3 million accident records in the US between 2016 and 2019. And the thinking here is to only use variables that would be only immediately known as soon as the accident is reported for a hypothetical use case of a GPS system or something being able to identify motorists currently on the road of any projected delay from an accident that's immediately known. So in my research, I discovered West Virginia and Arkansas to be geographic anomalies here. They contained a very disproportionately high rate of severe accidents, and so I decided to research these further. And with the model I ended up going with for my main goal was a random forest algorithm due to their versatility, general acceptance in industry, and my familiarity with them. So I was actually unable to earth very much at all about West Virginia, why they had such a high rate of severe accidents. It was very odd. I definitely was able to find something for Arkansas, but West Virginia still remains unexplained. But basically what I found here, so they both have pretty high rates of fatal collisions per driver per billion miles. So numerous sources indicate that Arkansas highways have high traffic volumes in general and also especially high freight volumes. And many qualitative sources indicate that these highways are also narrow and there's large chunks of national forest surrounding them. So here is a nice animation of traffic volume daily in the US. That circle is Arkansas. You can see it's a major spot of congestion comparable to any major city metropolitan area in the United States. So, and here is this map for freight, and once again it can be seen that Arkansas is again a spot of high volume for freight traffic especially. And those two forking highways that you see there, you go back, those two forking highways are the locations of almost all of these severe accidents. These are Interstate 40 and 30, and they both get very high volume. And here is the point when I decided to investigate these roads in particular, that I ran into a lack of quantitative information and had to rely on qualitative sources regarding these roadways. So Route 30 and 40 in Arkansas both get very high volumes of traffic, the busiest in the states. The busiest in the state by far are these two. And so I found some qualitative news sources indicating multiple projects to widen these sections of I-30 and 40. This one indicates that a major chunk of I-30 south of Little Rock was only 2 lanes going both ways, and comments indicated that these roads were very unpopular and had a reputation for being very narrow and containing lots of semi-traffic. So here is a map of Arkansas in particular, with these roadways and crashes indicated. These metropolitan areas, the east one is surrounding Memphis, Tennessee, right across the border. The middle ones are Little Rock and Saline County, which was the subject of that one news report indicated. And you can see overall many more of these dark dots for severe crashes, almost all along routes 40 and 30, and also several along the corridors of these roads passing by the national forests here. So obviously it's very hard to hypothesize any firm conclusions based on the lack of quantitative information, but the general thinking is a combination of high volume and high freight volume, and the highways ill-equipped to handle this may well be the cause of the high number of severe accidents in Arkansas, but West Virginia is still unexplained at the moment. All right, so the main event of my project. So before testing my model, I had to do some feature engineering here. So I dropped features with very little explanatory power and encoded and added in some more useful features. Basically encoded the road type, interstate, state, numbered highway, county highways, and added several more fields that were useful based on my criteria of information that would be immediately available as soon as an accident were to occur. So actually the data itself did present a problem with this model. It's extremely imbalanced. So the accident severities are on a scale of 1 to 4, and neither the data source nor the publisher of this data, there is no exact explanation of what these criteria are. Just a vague explanation of, oh, they're defined by delays caused. So I considered turning this into a binary classification problem, just lumping 1 with 2 and 4 with 3, given this lack of clarity. But I decided to move forward with multi-classification, with leaving this as a multi-classification problem. So my first baseline model, just to get a sense, is just a random forest model. Hyperparameters weren't particularly tuned in any sort of way. And so the first one was pretty unimpressive. It predicted the majority classes, 2 and 3 level accidents very highly, but completely ignored levels 1 and 4, 100% error rate. And this was with roughly balanced classes via oversampling and resampling these minority classes. So again, initial model, very inaccurate. And the overall 93.5 accuracy rate is highly misleading, so I kind of was at a crossroads here. So what I decided to do was I tried synthetically generating these minority class data points rather than resampling existing instances. So I used a technique that found the k nearest neighbors of these minority instances, chose one of these neighbors at random, and generated new points based on combinations of the attributes for these neighboring points. So this did produce much more promising results. Accuracy jumped to 53% for severe accident classification rather than 0. This was traded off for greater variance, much lower accuracy for predicting level 3 accidents, and level 1s are still being completely ignored, although this is not as big of a concern to me given what I'm trying to do with this model. So I decided more needed to be done before I jumped into fine-tuning this algorithm. So I did a text analysis of level 3 versus 4 accident descriptions. You can see the word clouds here. Level 4 looked to have a more even distribution of the most commonly words used, so I decided to dig more into this. So some very interesting finds here comparing the accident descriptions. Level 4 had certain words that were used much less and much more frequently than in level 3. You see some of them near, ramp, and slow are much less commonly found in level 4. And terms such as main, closed, street, and lanes were found much more frequently in level 4s. And some of these terms that were only found in level 4 are non-existent in level 3. So these can be used to engineer more useful features that further differentiate this class from the others and boost my model's performance. So my next steps are, as I said, engineering these features and fine-tuning my synthetic data point generation algorithm and my random forest algorithm. But please, I did a whole lot more work here than I did from my last checkpoint. So many steps were taken, lots of different things I could have done and can still do. So I highly value any useful feedback. I'm open to just about anything for this work, whether it be changing my model or anything really. And I suddenly found myself with a great deal more free time to implement these. So please give me your suggestions, and thank you for watching.